it's really a problem of success because we've got such a large supercomputer now that we're generating a lot more data, and so we're having to think a lot more carefully about how we access that data, how we make it available to people so that we can make best use of all of the new forecasts that we're providing. So, oops. So I'm going to talk about, say something about what the Met Office is, what's the problem that we're dealing with, how we need to think differently to solve that problem, what in the new ways that we're looking at using technology which mirror some of the things people have been talking about today, and what we're doing differently. So I'll start off then. So the Met Office, its primary function is to provide weather forecasts. We have a very big public weather service, and obviously the bottom line is we need to protect people if there's bad difficulties with the weather. So if it's bad weather, rainfall, obviously if there's going to be flooding, we work very closely with the Environment Agency to make sure the right information gets out to people to respond to that. We also give, there's a lot of information coming out at the moment about going to be hot in the next few days, over the next week, and people, that is great in some respects but can cause problems for some people, so it's a different form of problem. Also in supporting the economy, we provide weather forecasts, for example, to the airline sector. So we're a World Area Forecast Centre. There are only 2 of these in the world. We provide the forecast for the eastern half of the world, and the US provide it for the western half of the world. So basically, if you're flying above 20,000 feet, the weather forecast that your airline pilot is using is coming from the Met Office if you're travelling east, and from the US if you're travelling west. Below that, it's done by the National Met Services, but that's that's a good example of how weather forecasts are used in a much broader context globally, but not only to make airlines safe, but of course also to save on fuel. So in fact, in terms of reducing carbon emissions, making sure you carry the right amount of fuel on aircraft is really important. So if you're flying from the US to the UK, for example, there won't be enough fuel on the aeroplane to get you from New York to London. They're relying on the fact that they know the wind is going to help them along. So it's really important to get that right, obviously. If you don't, then they might have to land in Ireland on the way to pick up some more fuel. So that is, sorry, I'm doing this. So we, as part of our analysis of what investment is needed in weather forecasting, and in particular we have to use large supercomputers to do weather forecasting and climate research. There was an assessment of the economic value to the UK, and I think the economists said that there was a 1 to 14 ratio of benefit in terms of spend on what the UK gets out of it, and it's obviously very difficult to make these sorts of assessments, but some of the examples that I've just given you can give you a feel for the sorts of impacts, if you don't have the right information at the right time, the sorts of impacts that can have. So, as I say, that we had this big investment in the supercomputing, which it was delivered in 3 phases. The last phase was delivered last year, and that was a £100 million capital grant, and that was on the basis of these sorts of analyses. So well-being obviously is the other aspect of that. Just to say what the Met Office is, we are a part of government. We're owned by the business, it's BEIS, Business, Energy, Innovation and Skills. Industrial Strategy, sorry, the names change. But we're a trading fund, which means that as well as getting public money, obviously for doing our public weather service and the other services that we do, we also are obliged to sell some of our data and services in order to offset the cost to the taxpayer. So we don't have shareholders who are making loads of money out of it, or directors who get great big share incentives or anything. The money basically goes back to the Treasury. So some of it goes round in a loop, some of it comes in from outside. And that's it's a model. It helps us to have a much more customer-centric view than some government organisations because everything that we do has, the funding comes direct from that customer group. With the Public Weather Service, it's an interesting relationship because obviously not every member of the public can come and tell us what they want us to do. There's too many. So we have a Public Weather Service customer group who represent the kind of major users of the weather service, and they help us to scrutinise how we spend our money, so they will hold us to account to make sure that we're spending the money on the right things and delivering value for money for the taxpayer, which is obviously important. We have a very large proportion of our activity is science, so out of, I think there's slightly under 2,000 people in the Met Office, about 450 of those are scientists doing research and development. So a lot of that's involved in developing the models that we need for weather forecasting and climate. Some of it's involved in things like doing climate research to put into the Intergovernmental Panel on Climate Change. We have a lot of applied science, so we support many projects in developing countries. A lot of it is actually to encourage national weather services to increase their ability to do forecasting for themselves. Also, there's a lot of work looking at climate change adaptation, supporting people with seasonal forecasts so they can plan ahead for agriculture. A very wide range of activities that we do internationally, as well as many activities in the UK. There's a big push at the moment to produce the next set of climate projections, which will be produced at the end of this year, and those will deliver the climate change information that is then used to produce the climate change adaptation reports that the government needs to do as part of the Climate Change Act. All of the science is very well integrated into the information that government needs and other people need to make decisions. So there's quite a broad range of operational weather forecasts from day-to-day basis right the way through to what's going to happen in 100 years. We do all of that in the Met Office. I've mentioned commercial business already. And the international community. So just to say that the Met Office is part of the World Meteorological Organization, which is a UN body and represents, I think there's 190 different Met services, well as many as there are countries anyway. Interestingly, in terms of sharing data and electronically sharing data in real time, WMO was one of the first organisations that has really pushed this ahead of other sectors, because in order to do a weather forecast you have to have global information. So to get a good weather forecast you need to be able to, the whole atmosphere is interconnected, so you need all that information. So in fact Met services are fairly good at sharing information. When you look at hydrological services, for example, it's still very difficult to get people to share because it has, it's got geopolitical value to it. And so people often are very unwilling to share, particularly if you've got a dam in one country that affects the water reaching another country. It can be quite difficult to share that information between the countries for obvious reasons. And that makes getting environmental information about those sorts of things difficult. With weather it's easier. And of course you have satellite data which is global as well. But that international community is a very important part of what we do. I was going to say something now about the value chain and the kind of elements that go into creating a forecast and then how that turns into a decision. So the first thing we need to do is to monitor the atmosphere, obviously, and to then model and forecast it. The observations that we use come from everything from a Stevenson screen with thermometers in it and rain gauges with buckets in the ground, to the most high-tech satellites, weather balloons. All of these things are important. If you look at the impact on the weather forecast, the satellites look as though they have the most impact because there's so much data and it's global in scale, it's homogeneous, which means the models can use it very well. But without the ground-based observations, the satellite observations wouldn't be any good. You need something that you can calibrate against, and there's certain types of information that you can only get from these localized observations. So that's why we continue with observations of that nature, which obviously have been around for a lot longer. So this slide is really about some of the improvements that we've been making in our forecasts over the last few years as we've introduced the new computing. Now that if you might be able to see right at the very bottom, there, that little square there is the size of computer that we had before we had our upgrade. And then this was the first stage of the upgrade, and this is the second stage. I'm not quite sure why it's lost the bottom of the slide, the thing here. That's just supposed to show you the scale. So 1.2 petaflops, now we've got 16 petaflops. So if we look at, as I mentioned the observations, a big improvement that we made recently was in the radar network. So radar are used for measuring rainfall, and by getting better information about the rainfall, obviously that really helps us with the forecast. It really helps us particularly so people can see what rain is coming, and actually, if you're looking for the next hour ahead, sometimes just looking at our radar images, if you've got our weather app, you can see them, or on our website, and you just extrapolate that in your head, you can see what's coming in the next half hour or so. So that's important. A couple of years ago, we introduced a bigger domain for our forecast. Once we got a bigger computer, rather than having, so our high resolution model, we have a model for the globe which has around 10 kilometre resolution, so it's divided up into grid boxes of 10 kilometres. For the UK, we have a model that's 1.5 kilometres, but by having a bigger computer, we can run it, instead of just over the UK itself, we can run it over a wider area, which means we can actually get the boundary of the domain that we're interested in further away from what we're doing. So if you can see that picture at the bottom, you'll see the UK's in the middle there, and in the middle of that one. And so it means we're able to get the weather systems a bit better. So the global model was increased to 10 kilometre resolution in spring last year, and we also introduced new UK hourly forecasts. So you can already start to see here that we're getting, we've got bigger domains, higher resolution, more frequent forecasts. That's, it's escalating the volumes of data that you're dealing with all the time. And particularly this hourly forecast, of course, is an issue because it means your forecast is out of date within an hour. After that hour, you want to have the next one. You're not so interested in the previous one. And so that creates its own challenges. It's not just the volume, it's the speed of the change of the data that's important. We've also got better information about winds. We've got the new ensemble data forecast. So these are the ensembles, basically where we run a whole series of weather forecasts instead of just one, because to look at the uncertainty in the predictions. And we now run those out to 5 days. So that gives us a much better idea of the range of possible outcomes. And of course, the further out you go into the future, the more that becomes important because the more the forecasts diverge. The challenge then is how you get that information in a form that people can understand and use, because we're providing so much information. You don't just want them to pick the one that looks the nicest in terms of what they want it to do. You want them to actually get that real probability information. So, and then the other thing is increasing the vertical resolution. So that's, again, you can then represent the physical processes better. So things like convection, where you get very localized storms, you represent that better if you get the vertical resolution better. Just moving on. So what happens to that once we've done those forecasts? What happens to those? So we provide the information in a number of different forms. We provide it on the model. Well, it isn't actually the model grid anymore, but on a standardized grid, so people can use it if they're running some kind of modeling system, which over the UK, for example, that they can ingest our data in a form that's similar to theirs and combine it more easily. We also provide spot data, so when you look at the app and you put in your location or it finds your location, it's using that spot data, so it's using data at individual locations, and I think we have 10,000 sites for that now. We also provide the observations, obviously. One of the big areas is the warnings and guidance. So I mentioned about what happens if you've got flooding or heat wave or so on. So we have a system for providing those warnings, and more importantly, we have make sure that people can get that information, that it's provided in a form where everybody has access to it. So, for example, even though the BBC are not now using our weather forecast, they are using our weather warnings. So in fact, you'll hear them talking about bizarrely, you will actually hear them talking about the Met Office more frequently now than they did before, because they didn't always remember to mention that it was a Met Office weather warning, but they do now. That's interesting. It's all about communication, but it's when there is something that people need to respond to, it's really important that they have the same information, so that everybody is working together to deal with the problems. And we also provide kind of briefing services for people as well. So where there's critical advice that's needed, we have public weather service advisors who work with the fire service, for example, and other emergency services to make sure they understand what the forecast is telling them, and that they feel that they have the confidence to act on it. A few years ago, when there was flooding in Cumbria, we'd already improved our services really quite a lot, and we had good advice and everything. But the police didn't actually, and the fire, I can't remember whether it was police or the fire service, but they didn't actually put the boats and things in place to support people until after there was a bridge that collapsed and unfortunately a policeman died. It was only at that point. Since then, they've been much better at actually taking our advice and acting on it in advance, so that they put things in place in advance. And we've had, in recent events where we've had red warnings, people have closed schools before the weather has hit, so that people are not put at risk before the event happens. And that's obviously a critical part of this. So those sorts of things I'm talking about has nothing to do with the technicalities and the clever science that goes into weather forecasting. It's all about how you communicate and how you work with your partners to do that. And I think that's those human aspects that are important, and the data science aspect is really how we provide the data that supports that decision making. So it's how all those things fit together, really. Just to mention in terms of the drivers, I mentioned that the Met Office is a training fund, and so there's a bit of a tension within the organisation. Sometimes we find different bits of government, we've got one bit of government telling us we need to give all our data away so that everybody can benefit from it economically, and we've got another bit of government telling us that we need to maximise the return on our data so that we can give money back to the Treasury. So you can imagine that creates its tensions, and I've kind of reflected those in this diagram here, one of the things we need to do with our public weather service is to make sure we reach as many people as possible, which obviously the ideal way of doing that would be to give everything away for free because you reach more people. We need to make sure we're trusted. Obviously, it's no good providing a weather forecast that people don't, if people think it's wrong all the time. We also want to make data available in a way that will help to drive innovation, to encourage people to use it in new ways, in new sectors, perhaps where they're not using it very well at the moment, where maybe they scrape data off Google instead of getting the best advice from the Met Office. We need a service provider arrangement, obviously, if we're going to do that. Which things can you get for free and which things do you have to pay for? Is there a simple licensing agreement? And as I mentioned, revenue to offset the cost. And just a more broader thing really is, how can we make sure that social economic benefit, those big numbers that I showed you at the beginning, the benefit to the UK economy, how can we make sure that is really realised? So, actually I think I might skip that one, I've not got much time. So, we're also guided by the Inspire directive, which is a European directive, which I think it got a lot of attention when it came in, but perhaps less so now. But there are some useful ideas in that which we want to implement. I wouldn't say we've implemented them all yet. So there are a number of different aspects to that. We want to make sure that people can discover the data, so the catalogue is adequate, that they can view the data easily, and at the moment it's patchy what we can do, but we're gradually changing that. That they can download the data, that they can transform it so that they can use the data, reuse the data, and there's interoperability between different types of data. And ultimately, it would be good if we can do remote compute, and I'll come back to that last one right at the end. So what we're doing, we're just generating so much more data now that we're having to look at different ways of providing it to people so that we can achieve some of those aims. If you just look at the way that the number of floating point operations have changed over the years, so and we're extrapolating that to 2020, you can see the growth in the amount of data that you're going to be producing with the growth in computing power. So we've put if you look at the top, I don't know whether you'll be able to see actually, but we've just labelled it with the computers that we had over those time periods, but it could, the same would apply in any area where you're using computing, which is obviously increasing in power over time. So, and we upgrade our computers about every 5 years. So what we're aiming to do is we will keep our, certainly for the foreseeable future, we intend to keep our large modelling on supercomputers on premise. That seems to be the only viable way of doing it. There's an awful lot of performance issues. The interconnectivity that you need to do weather forecasting, because every part of the globe is connected to every other, means that we need a certain type of computing. That's obviously becoming increasingly challenging. The parallelization of computers is a big challenge to us, and there's a very big project going on now to rewrite all of our code to make it work better on the new emerging technologies, and also because we use latitude-longitude grid, which means as you go to very high resolution, you get stupid resolution at the pole. You get tiny grid boxes which just don't make any sense. So we're changing the grid as well. So a lot of processing will go on still within the Met Office, but we're also moving a lot of the data that happens outside of the model onto the cloud. And some of our post-processing as well will happen on the cloud. So that will allow us then to use some of the technologies that are being developed by other providers, so things like selling data, processing data, some of the algorithms that people are using. We'll be able to make use of those more effectively because there's a whole ecosystem of developers out there. And also other people will be able to make use of it better. So that fulfills a lot of the criteria. That discoverability makes it easier to find. It makes it easier to do visualization because there are tools out there. All of those things should be made easier. There are major challenges, of course. We haven't quite sorted out our pricing models yet. It's a very different way of working, which we're not used to and our users aren't used to. So I think if we were a new provider and we were just selling to a new audience, this would be a lot easier because everybody would come to the cloud to get the data. But we also have a load of existing customers, some of whom are going to take a very long time to change, and we have to be able to service their needs as well. So lots of those things that we're thinking about at the moment, but it's making good progress. So we've had competed the provision here, and we're using AWS at the moment for as our cloud provider. And we're aiming to use the cloud where we can, where it makes sense, but understanding what it can do and what it can't do. And we've had some sort of fairly meaty projects where we've used the cloud to do a number of things, different cloud providers for different projects, and so we've gained experience of that. So we've learned from our mistakes where if you don't actually manage how you use it, you can rack up vast costs. So some people are nodding their heads here. And we've done that. We've been there and realised we can't, that can't happen. We have to manage it very carefully. And so there are quite a few people in the organisation who have that experience. So we're going to make sure we put those mechanisms in place to make sure we manage that effectively. But all of these things are challenges, of course. So our weather app, for example, I think was developed on the cloud, and also I think we used Azure for we've got a weather observations website where people can put their own weather observations in from their, for example, if you've got a little amateur weather station in your garden, you can load it up with that, and that was done on a cloud system as well. I think it was Azure. So we've got experience of different cloud providers, which is obviously part of that. So we're keeping the science technology on the left-hand side, on the in-house stuff, and then the enterprise stuff on the cloud. That's the kind of principle. So I was going to say something a bit about our informatics lab now, just to finish off. So this is an innovation lab. It's possible that some of you may have come across it before, and I can certainly put you in touch with them if you're interested in some of the things that they're doing. They have a little website, informaticslab.co.uk, which is, if you just type Informatics Lab Met Office, it comes up. They're basically our innovation lab. We've put together scientists. We've got the building that we're in. We've got the scientists on one side of the building and the technology IT people on the other side of the building. They do meet in the middle, but not as much as we would like. In this team, we have mixed them together. So we've got a number of scientists and IT specialists. Many of them are people who kind of, bash against the constraints of the civil service. They think differently to a lot of other people, and actually this environment works very well for them. We also have a communications graphics expert in the team as well. So they typically don't have the technological expertise, and that's quite interesting because as well as bringing something different and obviously being able to visualize things better with using somebody like that, it also changes the dynamics of the team. What they found was they explained things more carefully and in simpler terms because this person's in the room, because they have to for her. But what they've actually found is they understand each other better because, of course, people assume that their colleagues understand what they're talking about because they're also technical, but in fact, often people don't. And so it changes the dynamics. They've experimented with different ways of working, for example, paired work, where people develop code in pairs, and they found that that was very productive as well, rather than working individually. So lots of those sorts of things, as well as looking at technologies and solutions. So they've focused on three main areas now. They've decided to really focus down on problems that the Met Office has as its core activity. One of the difficulties with an innovation lab is it can be seen as a bit of a luxury by other people in the organisation because they're doing experimental things. They don't actually deliver services, they deliver prototypes, and they get to play basically. And so actually if we can make it much more focused on things that still in that space of innovation but are very much difficult problems that the organisation has at its heart, it becomes much more relevant to everybody, and it's easier for other people to get involved. So there's a project going on which the lab are helping with, on looking at improving workflows for forecasters and scientists, looking at different types of big data engines, visualization, machine learning, and I'll come back to that in a minute. I've got another slide on that. And then there's another one which is interesting, which is looking at the physics in the models. So that's really saying, as the models get more expensive, are some of the parameterizations, which are using approximations anyway, could we use elements of machine learning to instead of some of the physical parts of the model? So if we take perhaps a very high spec physical parameterization like radiation and say, well actually we're not able to run it as high spec as we want in the model, but we can offline, you run that, you then use machine learning to emulate that and then replace the scheme in the model. So they've done some initial tests on that and found that it looks reasonable. There's still some work that needs to be done. I was talking to the chap that had been doing it actually recently, and he said he didn't think it would end up being cheaper, but what it would be able to do would be to replicate a much more expensive radiation scheme than they could afford to run in the model. So they would be able to say, for the same money you get something better, but it's a long way from actually being able to give the answer. And then the other aspect is the public weather service reach. So the number of elements to this. One is actually getting better information to the forecaster. So I mentioned that we're doing all these ensembles where we do lots of model forecasts, so to get the range of possible future outcomes, and you then have to try and make sense of that. What's the best way to present that information to the forecaster and to the public? But even presenting it to the forecaster is challenging, and let's get that bit right first. Because they can then interpret that and help people to use it, and there's a lot of experimentation going on that. So just coming back to the actually, I don't know how much time I've got left. Okay, I'll skip this bit. I was just going to come to this final bit here, which is a way that we're looking at how we can give people better access to the data. So this was a project that was started in the lab. At the same time, actually, there was some work going on in the US, and what's happened now is they've combined those pieces of work, so they're all working together. We called it JADE. It's now being called Pangeo because they've got more money, of course. It's always this case, isn't it? They were doing some really clever stuff here. In fact, they still are, but it took on the bigger name because so it's called Pangeo. It's got its own website. But basically what they're doing is taking some of the open source tools that are available, and the Pangeo site mentions some more than these, but some of you will recognise some of these, and in fact other people have shown them as well. And it puts them together in a way that helps us particularly for this domain. So it's particularly looking at the meteorology ocean domain. And So using some of the, for example, Jupyter notebooks to take, so people will be able to write a piece of Python code, put it into a notebook, into a container. It can then run on our data set in the Met Office and extract the bit of data that it needs, do the processing, take it back out again, protects the IP of both the Met Office and the developer, whilst they're able to interrogate the data much more easily. So as we move further forward and data sets get even bigger, this will allow us, well, first of all, to do more clever things on the cloud itself, but also actually to be able to bring the problems right into the Met Office instead of having to have all of the data on the cloud. So that it opens up a lot of possibilities. There are all sorts of challenges, of course, with this. It's using open source software, which, of course, has its own challenges. If you wanted to make it operational, it wouldn't be possible with the sorts of tools they're using here. There would need to be something that took it into a more operational level. But it's definitely the direction of travel that needs to happen. So the National Science Foundation are funding work in the US on this. There are commercial organisations as well as government organisations involved. So that's, I think, one of the interesting activities, which is a very technical but could have quite a major impact, certainly initially on the science that's able to be done with this data, but also ultimately on the way a wider group of users will be able to use it. And I'll finish there. Thanks.
With the Meteo Group taking over from you the
Yeah.
forecasting service for the BBC, do they use your who owns the sensors? I mean, do they rent? I mean, do you own the sensors and then you sell them the data, or how does it work?
The observations.
Yeah.
So the observations in the UK will be made by the Met Office, yes.
Yeah.
And we do use some observations made by other people as well. So some rainfall observations from the Environment Agency, for example.
So you sell to the Meteo Group.
So there is we also, as part of our public weather service, we also provide a public weather media service, which is free to all media companies and to all providers that are providing service to a media company. So Meteo Group could use our service for free. They choose to use their own service, which BBC then have to pay for. I know it doesn't make sense, but that's the way it's been set up. So they will be paying for the data. Yeah, but what they do for the forecasters, they take Met Office forecasts and European Centre forecasts and the American various forecasts from around the world, and they create their own blended forecast. And the observations, yes, they take. So all the different Met services around the world collect observations, and they are shared. And then those can be they can be used by the commercial organisations as well, but they have to pay for them.
So did you have to change the way you work, you operate? After the contract ended with the BBC?
We haven't changed the way we do our weather forecasts. I mean, we've improved them because we've got, we're always improving, and of course we've got a much bigger computer.
But I mean, the financial impact, let's say.
I would say that financially, we're probably better off without the BBC, because in fact it was costing us money to do the contract. They were a very demanding customer, and they didn't pay that much. I mean, the public weather service costs £97 million a year. You can obviously the BBC were only paying a tiny fraction of that. So it's not about. I mean, but reputationally it was not great to lose the contract, obviously. But it remains to be seen. The BBC not taking our forecasts is a risk for them, obviously. I think the fact that everybody is using the warnings is really important. So they are using our weather warnings, at least when they're amber or red. They don't have to use them when they're yellow. But that's important, because that maintains the credibility of everybody. That helps them and it helps us as well. So actually, I think we've probably got a better relationship now, because it's much more clear what the purpose of that is, and to make sure that we get it right. So.
Can I ask a provocative question? So, in government now we have AI. Every department saying AI. So, think of a future where computers get very, very large, and you just get a huge AI package, and you predict tomorrow's weather from today's weather without any differential equations, all, just a pure, just like learning to play Go or something like that. Is that a kind of future you're staring at?
I don't think so. I think for the first couple of hours, I think
For about 2 hours you could.
for the first couple of hours, yes, I think it probably is. And in fact, I have regular arguments with my colleagues about this because we have a program which is looking at what we call nowcasting, which is those first few hours, and a lot of that we do combine it with the statistical, with the observations, but it does use the numerical forecasts. And actually, the numerical for the first few hours, the numerical forecasts aren't that good because it takes them a while to settle down. They really come into their own after the first 3 hours. If you're looking a day or two ahead, then the weather evolves. It doesn't just move from one place to another. You can't be guided by what happened before. It's like you've got the physics is interacting. It's non-linear, and that it's the non-linearity really that does it, and the chaotic element of it. You really need the physical processes to be able to get a good forecast a day ahead, I would say, and I don't think that will change. It may be that in 20 years' time we'll be saying something different about AI, but I think it's unlikely.
Maybe
But I do think for the first few hours.
A mixture of the physics and the modern emerging AI.
So that's where we're looking at I mentioned about this example of replacing the radiation scheme with machine learning in the model. So there are certain elements of the model which have empirical parts to them in the cloud scheme, for example, where you can imagine that, because essentially there are empirical statistical things in there already that you could use those more. What I don't think it will do is replace the Navier-Stokes equations. I think that's. But if anybody manages to replace the Navier-Stokes equations by machine learning or AI, then let us know. I don't think anybody's done it yet.